Dimensional analysis refers to a specific problem-solving technique that we use pretty much all the time in chemistry. Anytime you have a problem that doesn't seem to fit any equations dimensional analysis is likely the best method to solve it. I'll walk you through two problems today, one single step and one slightly longer. For our first example, suppose you wanted to convert 14.0 inches into units of centimeters. And you know that 1 inch is equal to 2.54 centimeters. To start solving this problem, we first need to write this given equality as a fraction. Because 1 inch and 2.5 centimeters are the same, we can write two fractions that both equal 1 that might be helpful. The first has inches on top and centimeters on the bottom. And the second is going to have our centimeters on top and our inches on the bottom. But we only need to use one of these. And so the question is, how do we choose which? There are a few tricks that can help us in dimensional analysis. The first is that we will always start with our given input by itself. So in this case, we'll start with 14.0 inches. The second trick is to be very careful about including units with every number that you write down, which I've got here. Now, the process of dimensional analysis is really just a series of multiplications by fractions. Hopefully you remember that if something like a variable is present both above and below a fraction bar, it's going to cancel out. That really is the key to this whole process. If my input is in inches, then I need to use a fraction that has inches on the bottom next. That lets me cancel out my units of inches. So I'll put 1 inch on the bottom. And if I put my centimeters on top, then my answer will only have units of centimeters. So I'll multiply my 14.0 inches by 2.54 centimeters over 1 inch, which gives me an answer of 35.56 centimeters. Now, that number needs to be rounded properly with significant figures to a final answer of 35.6 centimeters, and then I'm done. You'll often see questions that require more than one multiplication step. In order to convert a density of, let's say, 3.26 kilograms per liter into units of milligrams per cubic centimeter, we don't have a conversion factor that goes directly from kilograms per liter to milligrams per cubic centimeter. What we can do then is break the conversion down into smaller steps. I'll start with my 3.26 kilograms over 1 liter. Since my units are a fraction, I'm going to explicitly write them out. Now, this question has two distinct parts. First, we have to convert mass from kilograms to milligrams, and then secondly, we have to convert our volume from liters into cubic centimeters. I'm going to deal with these completely separately, one at a time, and I'll start with mass arbitrarily. Now, I write my dimensional analysis problems out a little differently than your textbook does. The math is the same, the information is the same, the process is the same, but instead of using separate fractions, I like to use a set of boxes. So my given information is going into the top and bottom of my first box. And I'll just draw a line to make my box. It's possible to convert directly from kilograms to milligrams, but usually if both of your units have prefixes, it's far preferable to do it in two separate steps going through the base unit. That helps you from getting quite so confused. So in the second box, I need to have kilograms on the bottom and grams on the top. And I know from my metric prefixes that 1 kilogram is 10 to the third grams. All right, now if I stopped here, my kilograms are canceling and I'm just left with grams per liter. To get it into milligrams, I need to add one more set of boxes. So this time, grams have to go on the bottom so that they cancel with the grams up top. And I'm going to have 1 milligram on the top of this box. I also know from my metric prefixes that 10 to the minus third grams are equal to 1 milligram. Then my grams have canceled. At this point, my mass units are finished, so I can ignore it from here on out and move on to my volume. Now, I know that 1 milliliter is the same thing as 1 cubic centimeter. And I know that I'm looking for cubic centimeters. So if I can get my liters into milliliters, then I'm almost finished. Since liters is on the bottom of the first box, I need to have liters on top so that it cancels. And it doesn't matter that my liters are going to be several boxes apart. I'll just draw my line, and 1 liter is the same. Oh, nope, started to do that wrong. Remember that your prefix always goes with the base unit. So my conversion factor is actually 1 milliliter on the bottom and 10 to the minus third liters on top. If you forget that in the middle of something, you of course can erase it and carry on. Now, the very last set of boxes that I need is going to have 1 milliliter on top and 1 cubic centimeter on the bottom. Okay. Now, to finish up the problem, I just have to plug this into my calculator, and whatever it tells me my answer is hopefully my answer. When I've typed it into my calculator and I've made sure that everything is put in correctly, I end up with 3,260 milligrams per cubic centimeter as my final answer. I got that answer by multiplying every number on the top together and dividing by every number on the bottom. Most of the numbers in that example are ones, and so it's not the easiest thing to see how you want to enter this into your calculator. But let me show you a different example, and then we'll talk about how to use your calculator to help solve these. Let's say that I had units A, B, C, and D, and I wanted to convert 3 A's into D's. And my conversion factors were 5 A's are equal to 2 B's, and maybe 4 B's are the same as 3 C's, and then 6 C's are equal to 7 D's. So when I'm entering these numbers into my calculator, I can do it. There are 3 main ways that I'll tell you that you can use that will invariably give you the correct answer. The first method would be to explicitly type into your calculator 3 times 2 times 3 times 7 equals. That's going to give you some number. In this case, it's 126. In a completely separate step, then, I could do 5 times 4 times 6. Those are the numbers that are happening across the bottom. And that would give me 120. Then in the last step, I would need to type in 126 divided by 120 to get my final answer. And here, just like I've mentioned in other videos, it's best if you can just pull those numbers down in your calculator and not retype them. Regardless, I end up with 1.05 D's, whatever D unit is, as my answer. Okay, so that's one option. A second option is to make use of the parentheses buttons if you have those. So if I was going to use the parentheses, I would start by opening the parentheses and then typing 3 times 2 times 3 times 7. I would close those parentheses, then enter the division symbol, and then open a new set of parentheses and multiply everything on the bottom. And that again is going to give me 1.05 D as my answer. The last acceptable way that you could type this in without using parentheses would be to be sure that in front of every number on the bottom you have a division sign. So you would type in 3 times 2 times 3 times 7 divided by 5 divided by 4 divided by 6. That will also give you our answer of 1.05. What I tend to see a lot of students do is not strictly following the order of operations. Your calculator has a fanatical devotion to PEMDAS. And so what some people try to do would be to type in 3 times 2 times 3 times 7 divided by 5 times 4 times 6. That's the way that a lot of people would read that problem out loud. And so a lot of people try to type it in that way. When you type it in like this, however, the answer that your calculator will give you is 604.8. That's a far cry from 1.05. So when you're solving dimensional analysis problems, just be very careful that you're using parentheses or somehow designating that all of your bottom numbers are on the bottom of fractions.